Okay. So quantum computing is very nice, but what is quantum computing, right? At the beginning, we might think, wow, quantum computing uses quantum mechanics, but actually it's not the case. Semiconductor use quantum mechanics already. Your transistor won't work if there was not band theory, right? If you have done the device physics, electron and hole, without quantum mechanics, there's no hole in this world, right? There's no such concept. So laser quantum mechanics. Without quantum mechanics, you cannot have laser. So I just taught, same for physics student and for E student, all the class you have taken, it has relationship to quantum already. But quantum computing, some people call it quantum 2.0, is that you use two important quantum phenomena in the computation process. One is the superposition, one is entanglement. All right. So what is entanglement? It's like correlation. Some two particles, they through some process, they're coupled to each other. The information of these two particles is more than the sum of the individual information alone. So we will show some example later, right? Again, you don't know what I'm talking about entanglement, but at this stage you know, oh, entanglement is something important I need to pay attention to, right? But later we will have math to talk about entanglement. Same for superposition. It's just saying that a state actually is a linear combination of many states. And for those who have learned about wave mechanics, right, we always say, oh, these two waves come together. When they come together, the P is a superposition, is the addition of the two other waves. Or for electrical engineer, you remember the Fourier transformation, right? You have an electrical signal. And actually, that electrical signal is a linear combination of many different frequencies, sinusoidal wave. That is superposition already. It's as simple as this, right? It's just that how we harvest these two phenomena to do something very powerful. And in the past, not just that we don't know how to do it, but also that the technology cannot implement them because they're so subtle. In our real world, there's so much noise, they all get damaged. But now we can control the environment so well, we can harvest this phenomenon, right? So the point is superposition and entanglement. But I also say interference is very important. That is because any quantum state has a lot of information. You will find that you cannot get them in a reasonable amount of time or with reasonable amount of effort. And it becomes useless. So you need to be smart to come up with an algorithm, like the Shor's algorithm, that you do some interference between these states so it will single out the answer that you want. Okay? Just a little bit explanation for now. There are two types of quantum computing. One is gate-based, right? We electrical engineer really like this gate-based because we do work on logic gates in our circuit. So we thought that they are related. They are related, but they are quite different. We will see later. Basically, you apply some gates, not gates, Hadamard gates, identity gates, Hadamard gates, do some measurement, go through the algorithm, you get the answer you want. This is what we call, I say this talk, but also this class. Another is quantum annealing. And gate-based is like what? IBM, Google, Rigetti, they all spend most of their time here. Quantum annealing is actually just use some quantum qubit and to do some optimization problem. So what is annealing? Annealing is like, if you know, when you have a crystal, you have a steel, they might have a lot of disorder or defect. What will people do is hit them up and let it cool down slowly and eventually become a perfect crystal with very high quality. This is called annealing, right? So mathematically, when you try to optimize a problem, that's what people do also. They inject some noise or some so-called temperature to let the system go through this landscape. For example, this is not a real space, but it's talking about a configuration space, maybe how you rearrange the atom, and then you have different energy. So this is the global minimum at this point. So my goal is, maybe heat it up so it will go through here and eventually find the global minimum. right? Just imagine I want to find the valley of this mountain or this range. What will I do? I would just run around and hopefully eventually I end up in the valley if I don't have any map, right? Or let's say someone just jump, I have enough energy, jump to different places, hopefully eventually land at the lower place. This is annealing, right? But quantum annealing is that it can map to some problem and also allow some quantum tunneling through this barrier. But this tunneling is not a real space tunneling. But after all, it can help you achieve the problem, the solution faster. Makes sense? Maybe not, right? But doesn't matter. We won't test in the class. But the point is this: if you have our company, like D waves, right? They actually established much earlier than IBM's quantum group, I believe, or they commercialized earlier. NASA also bought a big machine from them. It's still not promising. They still have not shown any big advantage yet, but it's an active area of research. And you probably can find some account D waves, and they do quantum annealing. So sometimes you say, oh, they have thousands of 10,000s of qubits. They are not the gate base. Like IBM is planning to have 1,000 qubit, or they already have a 1,000 qubit, but they step back a little bit. They try to do intermodular approach and then continue to scale, right? But for this gate base, they're still below 1,000 qubit. For D-Wave, they have many thousands of 10,000s of qubit because they have different approach, okay? So we're talking about this gate base. So what are the applications? Why they're so important? I talk about optimization. I talk about entanglement. That allows us to do material and drug design, because if you go to any pharmaceutical company, they will tell you that they actually know how to find the best drug, but they need to keep calculating how to flow the protein, how the molecule should rearrange. Then this will be a cancer targeting drug or etc. That needs a lot of computing power. You cannot get it done by supercomputer. And if quantum computer works, then they can help you to find it. So that is very important. Finance, how to find the best portfolio. So if you look at the customer announced by some of the company, like D-Waves, you find that like I think Wells Fargo has a quantum computing team, by the way. Right? It's not useful yet, but they started already. Ford is a car manufacturer. Why do they do that? One is to optimize the dealership, optimize the logistics. Yeah, in US, so many cities, where should you have a dealer, and then where should I store the tire? What can I optimize everything? So it's all optimization problem, right? Secure communication related to quantum entanglement, okay? The message here is that superposition and entanglement are the enabling technology, and then we will talk about gate-based model, a lot of application. This one is easy to find, ask ChatGPT. So what is superposition, right? So let's talk about state. Any physics, anything has a state, right? People, how are you? Happy? No. Sad? These are the states, right? But anyway, in classical computer, we want to describe 0 and 1. We use the state of an object. We can use head and tail. That is completely valid. We can use head and tail to do computation. Happy and sad, right? But we cannot use transistor open and close. The switch, the transistor, turn on and turn off the gate. We represent the information by the state 0 and 1, okay? Now, in quantum computing, we have something called basis state, the fundamental state, okay? Like in 3D space, you have basis state of x hat, y hat, z hat. Any vector is ax hat plus by hat plus z, c z hat. Make sense? And these are the basic state, basis state, right? So we put in something called bracket notation. We will talk about this later, so don't worry if you don't understand. So in principle, I can say head and tail, happy and sad, or open and close as the basis state. There's no difference from classical computing. If you limit all the computation to only the basic state in a quantum computer, then it's as bad as a classical computer. What quantum computing show the power is superposition. So every state is a linear combination of two basic states for 1 qubit. So let me emphasize, this is 1 qubit, right? We will discuss more later what is a qubit, but here is 1 qubit. The qubit can be a state 0, it can be state 1, but it also can be a linear combination of state 0 and 1. And that is the quantum mechanics that always confuse people, right? So in principle, if I'm a particle, I have 90% probability in this room. I actually might have 10% probability in the room next door, right? For quantum mechanics, that is valid. So it's just like what? Like a spinning coin on the table. You don't know whether it's head or tail. For now, think in this way. Of course, this is not a quantum computer. Okay? Superposition is very important. And superposition is the linear combination of the basic state. So then bring us to the second topic. Not the same topic, but as another level. Now, then in a classical computer, let's say I have 4 bits. What can I store? I can store 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, right? So I can store 16 possible values. Are you all familiar with this? If not, you can ask me or go back to review the binary representation. 0, 0, 0, 0 is 0. This is 1, so I have 16 possible values. So this represents I have 16 possible basic states because now I have 4 bits. Okay? Now, based on what we discussed earlier, if I have 4 qubits in a quantum register, then I also have 16 possible basic states. So here, I remind you, for 1 qubit, classical is 0 or 1. Then for quantum computer, I have 0 or 1 basic state. So likewise, for 4-bit classical computer, I have 16 states. Then the quantum computer, I have 16 basic states, right? So what do I mean? Then it means I can have a general state like this. I call it psi. Again, you no worry about this bracket notation, but get familiar with it. I always have this bracket notation. It equal to what? I call it A1, basic state 0, A2, basic state 1, A3, basic state 2, right? A4, basic state 3, all the way to A16, basic state 15. Do you see what I mean about the general state? What's the meaning of linear combination? Any questions? While I can have all these basic states, but I also can have a general combination of this. Okay? Fine, if you are confused and you don't want to ask now, because we'll repeat again later. Yeah. Oh, very good. So this is a so-called Hilbert space. So we'll discuss later. So they can be complex number. So any complex number. So for example, 2 plus 2.5i. Yeah. Yeah.
Say earlier, the previous slide could be combination of 0 and 1.
Yeah.
But then here, combine. How do you know that? You see what I'm saying? Like, because either one of those states could be a 0 or 1, so that.
Oh, yeah. I know what you say. Is it? No, this is for 1 qubit. So for 1 qubit, you can only have 0 and 1.
Right.
For 2 qubit, now you can have 0, 0, 0, 1, 1, 0, and 1, 1. Okay. Because you have 2, right? It's just like head, tail, tail, head, tail, tail. But 0, 0 is 0. 0, 1 is 1. 1 0 is 2, 1 1 is 3 in binary. Yeah. So now I have 4 qubits.
Okay.
So I can have 0 0 0 0 or tail, right? And this corresponds to 0 all the way to 50.
Right.
Yeah.
So that, you're saying that here, you're saying that each one of those qubits is sure of the state, there's 0 or 1.
No, here I only talking about for this, if you have 4 qubits,
Yeah.
you have 16 basis states.
Sure.
The system has 16 basis states. I'm not talking about this 4 qubit as 0 or 1. I'm saying that they can have 16 basis states. And then the state of this 4 qubit is a linear combination of this. Okay, good. Thank you. Yeah. So I know it's confusing, right? This is not as yeah. Good question. But we will keep repeating. Okay. Any other questions? Yeah.
If you go back to one qubit, right? Then that qubit, the superposition can be represented by alpha, and beta type. How does this one qubit, the function of the superposition, somehow is being mixed up to come up with a 16 stages superposition?
So yeah, so this one actually, I need to say something here is an overview. This set of slides I try to give to general public in 1 hour, so cover a lot of stuff. So do not worry, do not think that I finished the topic of superposition already. Okay. Now then go back to a question. We will study that later also. But what I'm trying to say is that I want you to recognize that you just take it for granted now, right? For classical computer, you can have only 0 and 1 for 1 bit, right? How about for 2 bit? You can have 0 0, 0 1, 1 0, and 1 1, right? And so for quantum computer, this will be the basis state of that quantum register. And then the general state is a superposition of them. Okay, so there's a result. I have 4 qubits, right? So I can have 0 0 0 0 as one basis state, 0 0 0 1 as one possible as a basis state.
Why the superposition of 4 qubits should be the combination of the superposition of 1 qubit by 4 times, right?
Okay, so when you say 0 0 0 0, this is not a superposition. This is what you learn later, a tensor product, something called tensor product. You form a larger system. Superposition is saying that you add this basis state together with the coefficient in front. Right? So we are not doing 2 superposition. So the first thing, we form the basis state by the so-called tensor product. Again, we will discuss that later. We'll go through all the math. But superposition is that we have the basis after that, then we start adding them together. Okay. Yeah, so that's a good point. Then how do you change the coefficient? Actually, it is true because the so-called quantum gate is to move from one state to another state. And the difference between one state and another state is that you have different coefficient. And you are right, we apply a quantum gate. You get a what?
Other than 0,
Uh-huh.
then you're not the sum of digits. You see what I'm saying? Let's say I'm in both.
Yeah. So the square. Oh, okay. I'm going to tell you what that means later. Okay. Good point. Yeah. So let's go forward. I know. I hope that you don't drop this class right away. Okay. We have not really teach anything yet. I just want to give you a feeling. And this class is that we want to learn of this rigorously. Okay. So yeah. So now hand wavingly, you agree that we have basis state. Now, if I have n qubits, then I have 2 to the power n basis state, right? Because 1 qubit you have 2, 0 and 1. 2 qubit have 4. 3 qubit have 8. And then n qubit, you have 2 to the power n. So then it means that any general state is a linear combination of these 2 to the power n basis state. Make sense? That tells us what the power of superposition. We have not seen how to use it, but see how much information it has. If I have 300 electrons, each of them is a spin, right? So it tells spin up is 0, spin down is 1 as the basis state. 300 electrons, I have 2 to the power 300 basis states. Because the basis state are 0, 0, 300, 0, 299, 0, and 1, and then 1, 0, and then all the way to 300, 0, right? That is 2 to the power 300. 2 to the power 300 is what? 10 to the power 90. And to describe a state, a general state formed by 300 electrons, you need 10 to the power 90 complex number. And what is the meaning of 10 to the power 90? Right? Even Bill Gates doesn't really know how it means, even he's so rich. Our universe only have 10 to the power 82 atoms. And the number of bytes we have this world, including your laptop, your cell phone, your iPhone in your pocket, is 10 to the power 21. And imagine, how do we store all this complex number in to do complex computation? You say, I want to emulate 300 electrons quantum mechanical state. Basically, you cannot, because you even cannot store the state. Right? This is just to show you how big it is, the problem. You have a question? Yeah, so now you talk about I will cover that also. Let me see if it is. Yeah, it is actually next slide. So this again is hand waving. Now, so he's asking how you have superposition state. Is that you can do a computation? And indeed, this is a philosophical question. Quantum mechanics is linear. What does it mean? I apply a function to a general state, and this general state is a linear combination of 3 basis states. Then it means that it will apply to each of them at the same time, right? This one is not a rigorous formulation, but just to give you a feeling about the so-called quantum parallelism. A lots of algorithm, you actually create an appropriate superposition state, and then you apply a quantum oracle to do the so-called, and which is just a quantum gate, to do the computation. Then you get all the answer at the same time. But it is floating there. You cannot get it because you did not store it anywhere, right? But it done all the computation. Think about that. This is a naive or hand-waving experiment. Let's say this is calculating, let's say sine this number. Right? So instead I need to do sine 1, sine 2, sine all the way to 200 and 300, instead of doing 10 to the power 90 computation, I only need to do 1 computation. Because once I form this superposition state, all will get computed. But you cannot get it. It is over there, but you cannot get it. Right? So that is nice. So people also think this is nice. People try to explain what's the meaning of this. People may say, this is nice. Maybe we live in a parallel universe. Many things got computed at the same time. If you watch the movie, what? I forgot the name. All at once, everywhere, anywhere, anytime, all at once. The one, okay, anyway. Michelle Yeoh, who got the best actor or something. Yeah. Actually, it's like that. It's just, of course, that exaggerator, right? She lived in many worlds at the same time. Right? It's related. Okay, so quantum parallel. I hope at least you appreciate the power of superposition. It's not just that I do many things at the same time. It's that there are many things in one superposition state by just 300 qubits, right? Even kindergartner can count to 300, but no computer in this world can process 2 to the power 300 computation, okay? Now then, let's talk about the meaning of the coefficient. We talk about measurement, right? We want to get, yeah. Yeah. Yeah, that is here. So let's go back to 1 qubit, right? What will happen if we do the measurement? I want to extract the result. It's just like the spin coin. I want to know, this is not a real superposition, okay? Analogy only. I want to know what is head and tail. What will you do?
Stop it.
Yeah, you got to stop it from spinning, right? Very good. Then what will happen when you stop it? You either collapse to head or collapse to tail. And that is exactly what happened to quantum computing, quantum mechanics. Psi is a superposition of 0 and 1. I try to measure it. It will becomes either 0 or either 1. It collapses. That is called wave function collapse. Okay, this is a proper term. Right? So it collapses to 0 or 1. And then so if I get 0, what happened to 1? No more 1. Okay, if I measure 1, no more 0. But do I know what it will collapse to? I don't know. That's what Einstein said. I think you heard about that, right? He said the God doesn't play dice. He doesn't trust quantum mechanics is complete, right? But anyway, that is what happened. The only thing that we know is that the probability that it becomes 0 is proportional to the square of the coefficient in front of 0. The probability it becomes 1 is proportional to the magnitude square of the coefficient in front of 1, which makes sense. If alpha was 0, then it means the state is just 1, right? Because this is 1 times 1, right? Of course, I can never get 0, right? So let's have a lot of interesting thing. People say, okay, let's say macroscopic object also has superposition. Then where is the moon? The moon is everywhere. Every location is a state, and the state of the moon is the superposition of many states. The moon can be here, can be next to me, can be over there. And then the moon, when you look at it, you see it's there. It's just because you measure it, you observe it. When you observe something, you measure it, right? So when you look at it, it collapses to there. And that's why it is there, right? But this is difficult to talk about that. You can talk to your boyfriend, girlfriend, partner, whatever. Lots of romantic things you can talk about, right? But that is exactly the case for electron. Electron, when it is a wave, you measure it, it collapses to that point, and then you cannot find anywhere else, right? We don't go to those experiments, but I hope you understand in microscopic object, everything is a superposition of many states. Of course, it can be at a definite state, but if not, when you measure, it will collapse to that state. Okay. And now then come back to the meaning of coefficient. If this represents probability, then it means the square of this coefficient must be 1. Because when you do measurement, you definitely get one of the states, right? So the probability of getting any of these states, these basis states, needs to be 1, right? Sum them together.